Hi everyone, I'm going to present can LLM reasonable non-text modality in a training-free manner. So this paper was published on News this year, 2025, and I'm the presenter, Myung-Kyun Kang, MK. So before we go into the details, let's first discuss why multimodal LLM is needed. So actually the answer is very easy. So we also want to predict some LLM inference, not only use the text, but also use images, molecular, protein, and time series. And another thing that we can anticipate is that we can use foundation model to make our LLM prediction better. So how can we want to use non-text encoder to make LLM prediction better. However, unfortunately, multimodal LLM is super costly and expensive for their training. And also, we need a text modality pair for their model training. So, because of this issue, some scientific modalities, such as molecules, which contains lack natural text counterparts, making this kind of supervised alignment very challenging or sometimes impossible. So bridging the gap between the multimodality between the LLM is very sometimes impossible and very challenging. Because as I mentioned, the supervised training is so challenging, how can we detour the training part and perform the LLM as we want? So for that scenario, we normally consider in-context learning. So in-context learning, adopt LLM to the new task at inference time through the multiple example without additional training. So how it works is instead of just providing an instructional question to the large language model, we also provide multiple examples to the LLM to make final predictions. And because we provide multiple examples, the model will predict based on the given example that we provided to the large language model. However, we can easily capture their limitation because we can only provide text information into the LLM. So the specialized non-text encoder, all the foundation model cannot be integrated when we perform in-context learning. So let's summarize. So in-context learning, their major benefits is we do not require additional training to bridge between the multimodality and the text modality. But unfortunately, they only can handle text, so we cannot integrate to the non-text encoders. Multimodal large language model, they can use non-text encoders, but they need additional training to bridge the modality gap between the images to the text. And to fine-tune the projector, we need a lot of training resources, and also text pair data sets is required. The thing that want to perform in this research is they want to perform in-context representation learning. So this ICRL, in short, consists generally two parts. One is text level, is same as the ICL, in-context learning that we know. But what they want to further extend the ICL, they first extract some kind of multimodal input put into the foundation model and extract the features. And we also do project to the LLM embedding dimension and directly inject the vector into the LLM's input to make to perform inference. So because this is based on the ICL, so in context learning, no additional training is required. But as we use the vector from the foundation model, we can integrate non-text encoder for this ICRL. However, as you can easily capture, there is several research questions remain. So here's the research question that raised from this paper. Number one, how to make foundation model representation into the LLM without training. So this is this is the first research question. And if we project between two modality, what are the mechanisms behind in-context representation learning? And also, what factor really affects the ICRL performance is remained question, and the author want to give you the answer for these questions. So let's go into the details of the method part. So first of all, we perform all the tasks within the in-context learning scenario. As I mentioned, in-context learning not make prediction based on the question or instruction, but use multiple example as an input and make final prediction. So, but basically what they are doing is same as a regular LLM. So they take the text input and output text. The foundation model, so they take multimodality input and extract some feature vector. The multimodality can be images, speeches, and any kind of structured data set. And the projector is simple. So we bridge between the feature vector into the LLM token embedding. That LLM can process the vector and make a final output. Here's the data set they conducted their experiment. They conducted their experiment on molecules data set. And there is a 5 data set, and author performed their evaluation on this 5 data set, but you guys don't need to know about details. So basically, those data set trying to predict a certain continuous value, which means those 5 data set is designed for the regression task. And another thing that I want to just mention in this slide that in the molecules domain, we can convert these some kind of molecular sequence into the SMILES representation. So this is identical to these characters, the set of characters in here. So basically, we can convert those molecules into the characters, but yeah, I just want to be aware that when I say SMILES, which means the characters that represent some kind of molecular data set. So let's go into more details for the experimental part. So how we can inject the multimodal input to LLM in a training-free manner. So first of all, we can inject those in a text level. So as I mentioned, SMILES, we can convert this molecular into the SMILES sequence. And the SMILES sequence is composed of the characters, and character can be fed into the large language model token embedding, and definitely LLM can process. Another thing is PCA. So what the PCA exactly mean in this context is that we first extract the foundation model feature of the molecules and run PCA and stringify the PCA, which means after we run the PCA, we can change some foundation model feature into the certain series of value. And this number is also text and characters. We can directly feed into the model and make the LLM to make certain output. So these are text level injection way. And we can also inject some kind of representation in the embedding level. Number one, very naive way is zero path. Generally, foundation model feature contains lower dimensionality than the large language model. So we just add 0 to the foundation model feature and make a certain dimension that match to the large language model. And another thing is random projection. We can project the vector into the certain dimension using the randomly initialized matrix because it's just randomly initialized, but without activation. So the semantics are preserved. So we just change the dimensionality and just because it preserves those kind of big semantics. So we can still use those vector as an input for the large language model. Another way is optimal transport alignment. So this is slightly better version of a random projection. I'll provide one more slide for this. And for the ablations, instead of using the valid embedding, we can also put some random noise into the large language model to make this. But this is just for the ablations. So as I mentioned, what is the optimal transport alignment? So the major objective to apply this OT is how we can bridge the foundation model feature into the LLM token embedding. So to perform this OT, we need a 2 distribution. One is source and the other is target. And we set source to the foundation model feature, and we set the target for the LLM token embeddings. And what is the exact source of the LLM embedding? Because we can convert the molecules into the smiles representation or PCA strings, and we can also extract some LLM embeddings from the text. So we have one set of foundation model feature and the other set for the LLMs embedding, and we perform optimal transport OT magic, and we can get some kind of matrix that project from distribution source A to B. So what? And there's two variants they additionally perform for this OT. One is we directly set the foundation model feature as a source, and OT PCA means not only provide the foundation model in a raw, we after perform the PCA and set the source that PCA pre-processed for the source distribution for the optimal transport. Why it matters? Because we can reduce the demand distribution mismatch between the source and target. And the another advantage is because we set the target distribution explicitly. So the projected value is much more LLM-like. So some experimental details for all experiments done in this paper was use LLM 3.1, 70 billion instruct. And for the foundation model, they use Unimol. And the PCA target dimensionality is 20, which means they use the number of shots for 20 for the in-context learning. And some kind of details for the projector, they untrain and trying to not use activation function in the projector matrix. So now we're going to more details for the result part. Here's the result. And the first observation they found is the text level PCA outperforms other embedding levels method and ICL, which means, first of all, as I mentioned, we can convert the molecules into the set of character I told the smile. But instead of using the smile, the PCA of the foundation model performs better than using the smile representation. This is their first observation, which means the foundation model, although we directly inject the foundation model feature into the model, but string phi PCA value can be a valuable source to perform the ICL. Second observation they found is they said the OT-based approach shows really similar accuracy that we've obtained in the PCA, indicating that although they do not exceed the performance of the PCA, but they have similar accuracy. But why there is advantages? Because OT-based compared to the PCA, because PCA takes the text as an input and make a prediction, which means requires multiple tokens to make a final prediction. On the other hand, this OT-based all embedding injection method takes the context within a single token. So there is very low number of tokens that provided to the LLM to make a prediction. So which means, although they have similar accuracies, but they are much more efficient. Another result they shown in this paper is we can also perform this in-context learning, not only using the text alone or embedding alone, we can fuse both information to make a final prediction. So here is the first observation they found. So smiles with embedding level injection or any level of injection outperforms the smile only ICL, which means because the smile, as I mentioned, is the primitive way to express the molecules, we can add additional information to the model to perform some prediction. Generally, the performance goes up. So if we can provide some information into the LLM, and we can expect or anticipate better result. Second observation they found is PCA OT-based method performs really good and embedding level alone experiment, but when they fuse with the text level, I mean the smile, their performance is not very good or outstanding compared to what we observed before. And number three observation, interestingly, the zero pad just delivers very superior result in most cases. So although we do not apply super like a fancy way to map those into these LLM embedding, but we fuse with the text and the embedding, we can obtain quite superior result in most cases. So what is the finding? So first of all, as I mentioned before, the OT-based method, which shows best accuracy on the ICRL, when we fuse with the text, their result is not consistently optimal when we integrate with the text feature. So ZeroPath shows quite higher accuracy compared to the OT-based method, which shows best accuracy on the previous experiment. And the author trying to analyze this kind of phenomenon, and they first show up the attention map of these of the models and found that the representation we injected do not show high attention value. So if we provide two information, one for text and the other for the like a multimodality, LLM tends to ignore the injected vector and treat it as like a secondary. Although it's a beneficial, but since there's not high attention, that what we anticipated. And the author go more details about what factor actually impact the performance. The first observation, they found that they're trying to give the clue of their insistence. The first of all, if the projected foundation model representation is closely resembled to the corresponding text embedding, generally performance goes up. Definitely this PCA, because they extracted the value from the LLM embedding, so definitely it has higher similarity. And as we expected, OT-based, we use the target distribution. They have much more high similarity compared to the foundation, the LLM's token embedding representation. On the other hand, the ZeroPath, like a random projection, they shows really similarity. So the first one, they want to say if the extracted vector they injected to the LLM is really close to the foundation model embedding representation, we can get a higher result. Another important thing they noted in this paper is high similarity between the ICR representation generally degrades the performance. So another important thing is not the similarity between those token embedding, how the extracted vector is distinct between each other. So random projection or ZeroPath, those features are so similar to each other. So it's really hard to LLM to capture the differences among the feature that in the in-context example. So their performance goes down. On the other hand, our OT embedding based shows much more low similarity, which means they are much more distinctive that can be easily distinguished by the LLM, result better accuracy in ICRL experiments. And based on the experiment, the author trying to summarize these kind of all the phenomena. So first of all, embedding only. So when we only inject embedding into the LLM, it seems like LLM should perform this task as a task learning mode, which means LLM must learn certain tasks from scratch inside the prompt. So to support this argument, they perform ablation. So if there is a few example provided to the LLM, the prediction is almost close as random. So when the example goes up, the performance significantly improved. So indicating that because they need to perform some kind of learning during the inference time using the prompt. So we need a multiple example to perform this learning task. On the other hand, in the text level injection, it seems like actually the model do not require to learn during the inference stage. So which means rather than learn from the prompt from scratch, learn from the prompt, instead the LLM trying to retrieve prior knowledge they already know or they're already familiar with. So although they increase the number of shots, this PCA dimension means number of shots. Although they increase the number of dimensions, the performance do not significantly improved. But as I mentioned before, although the embedding-based method requires a lot of shots for to make the prediction reliable, they use really small context space, which means example for a single token. So although we can increase the number of shots, but still it's still not that much computational intensive. The author trying to argue that their methods quite valid compared to the previous method. So as I mentioned, generally, there's multiple methods proposed in this field, and they require significant a lot of resources, but compared to their approaches, because they only need to perform the PCA using the CPU, so they are much more efficient and sometimes even surpass the lightweight tuning pipelines. So this is they want to say they are not a super best method, but actually very practical way to, and sometimes even surpass. And another experiment they conducted is, does that even surpass some lightweight trainable projector approaches, which means there is a data set LPM24, which consists of molecules with the captions. And because they have a caption pair data set, they perform like a caption-based pre-training, or we can also conduct some kind of contrastive learning. Also, we can do both. And they're trying to compare those approach, whether their method performs better or not. Interestingly, the model only the model only fine-tune the projector using those data set does not show high accuracy compared to their OTPCA or OTPCA-ICL approach, indicating that in some domain, although we can perform supervised learning to learn the projector, sometimes their OT-based training-free approach even exceed the accuracy they obtain based on the trainable way. And following question everybody will have is, does that method also can be applied to the general cross-modality, like images? So here's the result. ICR actually underperformed a large supervised model for the vision and the audios. So basically, as you can see, all the values are not that super high that we obtain in the vision domains, but in some imaging modality, which is really hard to obtain, maybe this kind of approach can be a practical alternative way to perform this ICRL or ICL when the multimodal LLMs are unavailable and really hard to make. So here's the conclusion of this paper. First of all, ICRL enables training-free multimodal reasoning, which means training-free is super important. And also this can be a very practical, lightweight, and efficient way for the supervised training method. And some observation they found, text with embedding level injection is very beneficial. And also high similarity between ICR representation, degrade performance, and if the performance improves when the foundation representation is really closely resembled to the text embedding that LLM had. Okay, yes. This is the last. Thank you for your attention, and I'm very happy to answer any question you have.